Hello and welcome. This learning module is about maintaining adequate blood pressure for perfusion, where the key homeostatic mechanisms involved in blood pressure regulation will be discussed. For the human body to function, its internal environment must be monitored closely. Thus, the body maintains internal stability by compensating for internal and external environmental changes. Homeostasis is the state of equilibrium within the body's systems. There are numerous systems working in conjunction with each other to maintain this delicate balance. One of the ways this is done is through feedback loops. A feedback loop is a mechanism that the body uses to reverse a disruption to its equilibrium. Think of the body as a delicate ecosystem. Ecosystems rely on the balance of their counterparts and their ability to adjust to changes to survive. Likewise, the human body must be able to adjust and reconcile changes in its vital functions to survive. Feedback loops are comprised of 5 key moments within the loop. First, a stimulus will disrupt homeostasis in the controlled condition. Receptors will then monitor and identify the disruption and send nerve impulses to the control center, which receives the information and then decides an appropriate response. Next, nerve impulses will be sent from the control center to effector cells to enact a response. This loop will continue until the controlled condition is returned to homeostasis. Blood pressure is a controlled condition that is essential to many vital bodily functions. Blood pressure is the force exerted by the blood on the walls of the blood vessels. It is determined by 2 factors: cardiac output, which is the amount of blood pumped from the left ventricle per minute, and peripheral resistance, which is the vascular resistance to the flow of blood by the blood vessel. A stimulus such as dehydration results in a drop in blood pressure, which decreases the controlled condition, disrupting homeostasis. Baroreceptors in the walls of the aortic arch and carotid sinus measure blood pressure by detecting stretch in these vessels. These receptors will then send action potentials through nerve impulses to the cardiovascular center in the medulla oblongata of the brain. Once the brain detects the decrease in blood pressure, it will then initiate a response via the sympathetic nervous system. The brain will send action potentials which result in hormones being secreted by the adrenal medulla, which cause constriction of the blood vessels, which will increase peripheral resistance. These impulses will also increase heart rate and stroke volume, which results in an increase in cardiac output, meaning there is more blood pumping around the body. This combination of effects will result in increased blood pressure. The baroreceptors will detect this increase and continue to send action potentials to the brain until the blood pressure is adequately adjusted, thus returning homeostatic balance.